Um, we're going to assume in the beginning, that the actual object doesn't lose energy and it would make it back up to the height it started at. And if you've seen Newton's cradle before, Newton's cradle is an example of this. That's a transfer of energy and momentum. Every time the object hits a bead, the other side, the bead pops off. Then the bead comes back, hits a bunch of others, and it pops off. And in those collisions, there's very little energy loss. So we're going to see how that affects it here. Thank you, Gus. Thanks very much. In this example here, or in this theory here, rather, we can see the example we just looked at is this first one here. Okay? It's really this concept of conservation of energy, but we have to consider the fact that without energy loss, right here, at Q, the object would have returned right up to the dropper's nose, or Joe's nose, wherever he was standing there. It would have returned right to that height, but we have this energy loss, which we're going to call Q loss. Q loss. The concept here, though, is that there's always a total of energy that doesn't change. So let's take a look at that example one more time with numbers here. Yeah?
So if there was no air resistance anytime, would there be no energy loss?
Yeah, it would just be changing. It would be all potential, all kinetic. All potential, all kinetic. And it would simply go back and forth forever. Like ever and ever and ever. Physically. Yes? Where does the energy loss?
By your resisting those two.
Usually thermal energy actually. So air flowing over the surface of something will change its temperature. So the energy is converted into a temperature change, which is thermal energy either going into or out of the object. Usually the thermal energy comes out of the object because it cools it down. It's as if it's like evaporation in a sense, you know? Evaporation is a function of wind speed or velocity on a surface. If you have water sitting somewhere overnight, it will eventually evaporate. But if you have a fan blowing on that surface where there's water, it'll evaporate much quicker. So the velocity actually changes the temperature of it. So it's mostly going to temperature loss or temperature change. But there's also some heat generated at that joint at the top where the metal is rubbing against the metal. Okay, but it's very little. Did you notice that with this? Did you notice with this pendulum? When we dropped it, Joe, where are you? It came probably this far from your face, right, the first time?
Yeah.
It wasn't too far. So there's very little energy loss with something like this. Yeah, I mean, if we actually let it go for a while, it might swing through 100 times before it actually stops. You're losing very, very, very little energy each oscillation. As opposed to this example we've been doing over and over, right? The minute I release this, the energy is lost right away. I'm giving it energy. Why is it losing energy right away? There's a lot of friction between this material and the metal. If I instead take one of these carts with Teflon, I can easily go like that, and it barely wants to stop. I didn't give this much more force than I gave the eraser, but this went for a while because there was very little energy loss along the way, low friction. So low friction is low energy loss. That's the example of a pendulum. If you've seen a grandfather clock work before, it is not working on its own accord. A battery powers the clock to keep it in motion. But gravity does a lot of the work too. Okay, gravity does a lot of the work. If the battery died though, the pendulum would eventually just stop. It might take longer than what I just showed, but eventually it would just stop. It's like your arm. Now, what I want you to consider is that if I start a problem with a certain amount of energy, take a look where I'm highlighting, please. If I start a problem with a certain amount of energy, I have to end that problem with the same amount of energy. That's what this theory says. The amount of energy is always conserved, conservation. You start with a certain amount of energy, you have to end with that amount of energy. Okay, that's what we're seeing here with this. Now, where can some of that energy go? Into that value Q. What does that big symbol mean again? That capital looking E thing. Sum. So this is saying the following. I'm going to point and talk. This is saying the sum of all the energies in the beginning of the problem, initially, equals the sum of all the energies at the end of the problem, final. So this is initial, this is final. So if I'm thinking about a pendulum, maybe this is the beginning, and this is the end at the bottom. So call this initial, call this final. The energy at the beginning equals the energy at the end. I could call the end of the problem when it gets back up to here. and call that final. It depends on where you cut off the problem. We've done this already with projectile motion. If you toss something up, we can look at the way up, we can look at the way down, or we can look at the way up and the way down as one motion. There are 3 ways to truncate it or break it up. Very similar here. I could think of the way from the top to the bottom as one motion. I could go from top back up the top as motion. I could go from beginning all the way through, and that's one cycle. It depends on what I'm doing in the problem. I could call the end of the problem, hypothetically, midway point. Yeah, it's going to get back up to here maybe eventually, but in red, that's like a midway point on the way back. It's not drawn perfectly to scale. Please try to draw this symmetric. Okay? This black bob here on the right should be around the same height as the other one. So maybe go a little bit further so it's around the same height. And it should come back up to the height it started at. But this red one is like some halfway point or some point along the way. Okay, some point along the way. That's what the red one is representing. So at any point along the way, though, the energy is the same. So let's say I raise up this bob, and as Joe did a minute ago, you brought it up to his chin. It gave it some potential energy in the beginning. So in the beginning of this problem, we know that there's potential energy in the system. As it falls to the ground, and first of all, where's the ground here? From last class, what should I call the ground? Where's the ground? I saw his hand shoot up. Somebody else, you got the last one. Help me out, go ahead.
Is it the one that's below the middle?
How come?
Because that's like the ending.
Careful, don't say ending. Because any point could be the ending. You're on the right track, Rick. I need a reason.
It's the lowest one.
The lowest point, remember? We'll call the lowest point that this object can actually get to potential energy equals 0. Okay? The lowest point. So that is the 0 energy line. That is ground level. So when it gets to the bottom of this path, it has velocity, but it no longer has any height. If there's no height, what can I say? If there's no height, what can I say?
There's no potential energy.
Very good. There is no potential energy at the bottom because there's no height. So what energy must it all be at the bottom? Chris? Kinetic. Oops, let me use a different color so we can see that better. Okay, it's all kinetic at the very bottom here. How about the halfway point in red? How about in red, Chris? If it's exactly halfway, agreed. But in general, what can we say? It's part of? Yeah, it's going to be partially both. Very good, Chris. So at this point, it's both potential and kinetic. Why can I say that? Because think about it. It's still moving when it's in red, and it now has some height, right? Motion means kinetic energy. Height means potential energy. And in red, it has both motion and height. Therefore, it has both energies. And when it gets back up to where it started, it has to stop, doesn't it? Take a look where I'm pointing. It has to stop when it gets back to the height it started. So what's the kind of energy it must have here? Only potential, because it has stopped. So look at the balance of energy here. This is the best prime example of conservation of energy. Give me a number between 1 and 20. I don't care what number. Any number. Thank you. So we have 17 joules to start this problem. That's how much energy we have. At the bottom, if it's all kinetic, how much energy is kinetic at the bottom? If we have 17 to start. No? In kinetic, there's 0 potential at the bottom, yes. But conservation tells me what? It's still 17 total, but it's all kinetic now. It's all kinetic. What about this point in red? It depends on where it is. And we're going to see that in a little bit. Chris already kind of answered a question that we're going to answer in like 10 minutes, so he's way ahead. If it's halfway the height, it's going to be half each. But hypothetically, let's say it's like 6 joules of potential. it would be 11 joules of kinetic. Take a look at the balance of energy here. If 6 joules are potential, then it still has 11 joules of kinetic. But what's the sum of these two? What's the sum? It's still 17. It's still whatever you started with. So what's the energy over the far end over here? Still 17. Okay? This concept here is extremely important. Now, in the problem we just demonstrated, it clearly isn't the case. It might have lost a half a joule every time it passed through the equilibrium position, every time it passed through the bottom. So after the first run, maybe there's only 16 joules left. Then there's 15, then 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, no energy. It stops. So what's happening every time it passes through? If we're losing energy, that's Q loss on the far right. If I do this, think about it mathematically. If I start with 17 joules and I only ended with 15 joules, where did the two go? They had to go somewhere because you can't just disappear. It has to go in to the energy lost. So that would mean that the energy loss would be 2 joules in the system. So if you ever end with less energy than you started, God bless you, there must be friction involved or you made a mistake. If the problem says there's no friction, you better end with what you started with. If the problem says there's no friction, you end with the same energy you started with. But in this example, take a look, 17 equals 15, that's not true. Where's the missing 2? Plus 2 at the end is Q loss. So traditionally, let's write this down please. Traditionally, this Q loss is the work done by friction. So sometimes, and we're going to see that in one of our math parts here, we'll look at this equation to find the work done by friction. Work is FD cosine theta, and friction, if you recall, is mu Fn, and then d cos theta is there still. Look at the pendulum still, guys. It's still moving. So it's losing very little energy every time. It's still moving very little bit at a time. And this probably will go on for a couple more minutes because it's not losing all of its energy. Eventually it's going to stop until somebody does something like that and it disturbs it or there's a shake in the ground of some sort. But it is still slightly oscillating back and forth. Okay? Any questions on this idea? Can we press on? Okay, I'm going to show you numerically what we... So I just did the first one. So you don't have to write this all down again. Conceptual, the pendulum swinging without friction, that's what we just did on the previous slide. So we're going to jump down to the egg part. So take a look at this data table for the egg. This is an egg. It doesn't matter what it is. Call it whatever you want. Okay, it does not have to be called an egg. So this is a numerical example here. A numerical example. Do me a favor real quick. Cross this out and make that 0.04. This is out of your old textbook before I got the new book. I hate this data table. I don't know why they go to the nearest thousandth here. It just throws off the numbers and everybody gets confused later on. Cross this off right 0.04. Now, what I want you to pick up on though is recognizing that the energy is always going to be a constant in total. The energy is always a constant in total. So when you drop an object, what kind of energy does it have to start? When you drop it, you're about to drop it. What kind of energy does it have right now? All potential. Take a look, please. Potential. Any kinetic? Nope. The whole system energy is 0.74. Write a little note. This is the total energy. This column is total energy. Mechanical energy means total energy. When you see ME, you're being asked about the total. It's in your homework also, so I say this. When you're being asked about ME, it means what's the total energy. So you have only potential to start right here. The total energy is potential. It's all 0.74 of potential. There's no velocity because I'm dropping it from rest. From a height of 1 meter, no time has elapsed because I haven't dropped it yet. I drop it along the way down, 1/10 of a second, 2/10 of a second, 3/10 of a second, 4/10 of a second. It starts to lose its height, doesn't it? When it loses height, what kind of energy does it therefore lose? If it loses height, Andre? So take a look here. As the potential, or as the height goes down, the potential goes down. They go down together. They go down together, those values. But as it drops, what does it pick up? It picks up, Chris?
Kinetic energy.
Yeah, why? Why does it pick up kinetic energy? What is kinetic energy a function of? Not height. Not height. Kinetic energy is a function of motion. And look at the speed. The speed is increasing. Therefore, the kinetic energy is increasing. So as it falls down, we have an increase of speed and kinetic energy. But recognize, please, and look at the numbers. Add them together every time, you get the same total. 0.7 plus 0.04 is 0.74. 0.59 plus 0.15 equals 0.74. 413374. 16 plus 58 is 74. Every time we do this, this is going to sum up together to equal what we have, if I think about it like this. Okay, every stage along the way, the sum of all the energy at any moment is consistent, is constant, is not changing. So if I drop an object, or if I drop a pendulum, and it goes back and forth, it's really the same thing. At the top, it's all potential. At the bottom, it's all kinetic. Halfway in between, or part of the way in between, it's partially both. What's half the height, everybody? What would be half the height it started at? What number? What do we start at? Look at the data. Yeah, 0.5. Half the height is 0.5. And take a look. 0.56. Ooh, that's close. If it was 0.5, what would you notice about these energies? What would they be relative to one another? Call it out. They would be equal. If you are at a height of 0.5, these would actually be equal. You'd have half potential, half kinetic. Because if I have 10 joules from this height, and I get to half my height, now I have 5 joules of potential. Where did the other 5 go? Kinetic. Half the height means half the energy. So if you start with 10, now you got 5. The other 5 has to be kinetic. Okay, let's take a look at example mathematically. Imagine you have a little bit of a ramp here. So if any of you have ever been on like a skateboard or a bike or rollerblades, and you like to go over, you go off ramps and tables and tricks. And this is a person going down a ramp. It could be a half pipe, it could just be a ramp, it doesn't matter. So let's draw ourselves a picture of a ramp. All right, there's my ramp. It says that a child slides down a frictionless ramp on a skateboard starting from rest. Here's said child on skateboard right here at the top of this ramp. I think there's a really big ramp for that kid to be that small. So there's the ramp itself. Actually, it's 4 meters high, so maybe it's not that big. Whatever. It's a really small person. So a ramp of 4 meters. Why do I label 4 meters on the side there? Why do I label 4 meters on the side? Because I feel like in the other class I asked people to label this, and a lot of them labeled this as 4 meters. Chris, what do you got? Yeah. For potential energy, we need the Y value, and in this problem, it says the height of the ramp, not the length of the ramp. Write that down, please. Length of a ramp would be the hypotenuse. And then you can use trig at an angle and find the height. But Chris is absolutely right. You need the height change for potential energy, not the distance traveled. The distance traveled is the length of the ramp itself. Okay, this is not, oops. This is the length of the ramp, not the height. But if you had theta and the length, you could figure out the height. So keep that in mind in case that pops up on a homework problem. Okay, if you're given this as 10 and this is 20 degrees, you could find opposite of hypotenuse is sine. So you could do that. Anyhow, the question says, what is the speed of the child at the bottom of the ramp? How do I do a problem like this? I think about energy. I think about energy. Energy tells me the following. I can't lose energy along the way. So whatever I start with, I've got to end with. So let's label the type of energy I'm starting with. What kind of energy does this problem begin with? What kind of energy does it begin with? What can I fill in? I got 3 hands. Good. Rick, good. Potential. This person is at the top of the ramp to start. So as I write this to start, I can cross off kinetic because there's no kinetic in the beginning. Some of my students in the past really do like to write it down like this every time, and then they cross off kinetic and it's not there. You can just not write it also, right? I want you to understand that. This is like I'm writing it every time and then I'm just crossing it off. What about at the end of the problem, when he's at the end? When the kid is at the end, he's got velocity now. That's what we're trying to figure out. Does he have any more height? Does he have any more height?
No.
What do we have to make assumption then of James if he has no height?
It's all kinetic energy.
It's all kinetic. So where's ground level, James?
The bottom of the ramp.
Good. So we need to draw a ground level to make that next statement. So let's write that in here. So at the end of the ramp, he or she, said skateboarder, has no potential energy. But the skateboarder does have kinetic energy at the bottom of the ramp because the skateboarder is moving and we're trying to find out the velocity at the end of the ramp. Now, you might be a little bit stuck if you're trying to go ahead because you're not given the mass. Notice that? Anybody see mass? But doesn't potential energy have mass in it? What's the formula for potential energy? Formula. Yeah, potential energy.
1/2 mv squared.
That's kinetic energy, 1/2 mv squared. How about potential? mgh or mgy. Notice both of those formulas though, Ricky told us kinetic, Andre told us potential, they both have mass. So how are we going to do this problem if there's no mass given? If there's no mass given, how are we going to do this? Come on, take us. Yeah, go ahead.
You use the formula because you have the height of gravity.
Okay, so give me the formula. Let's fill it in.
Mgh
And then the other half.
equals,
I'll write it for you so if you don't remember. Okay, there's the formulas, James. See what James is doing? He's saying potential energy in the beginning is mgy in the beginning. Kinetic energy at the end is 1/2 mv squared at the end. So it's fine, and that's initial. He's right. I would start by doing that. What do you notice now? What do you notice? Mass cancels. Our answer is independent of mass. Mass cancels. I'm going to multiply by 2 on both sides. I'm going to kind of skip down to here. Multiply by 2 to get rid of the 1/2, and then take the square root. Multiply by 2 and take the square root. So for those of you that in the past have really always plugged in numbers, this is the case where you can't. You can plug the numbers in once you cancel mass. So write yourself a note right here, please. Write yourself a note here. At this point, you can plug in numbers. But prior to this point, can you plug in numbers? No, because mass is unknown. You can't plug in for mass if it's not there. So once you cancel mass, then you can plug in numbers if you want. But you do need to start with the formulas for this kind of a problem. Now, let's point one last thing out before we get to the next example. What's our governing equation for these problems? Governing equation. I've used that phrase before. With forces, what was our governing equation? F equals, Chris? MA. F equals MA. What's the governing equation you think going to be for all these kinds of problems? The governing one is the one that we begin it all with, right?
4 times the distance.
No? That'll come into play a role for when we do work. Work is force times distance, right? Look at the problem. Just look at the problem literally. What's the thing that it all stemmed from? It all comes from one thing.
Inertia equals 5.
Yeah. MEI equals MEF. Write yourself a note here. That is your governing equation at the very top. That's the equation that's given on your formula sheet. I do not give you PEI plus KEI equals PEF plus KEF. That's not given on the formula sheet. MEI equals MEF is given. You need to identify the types of energy that exist at the beginning and at the end. That's up to you to decide. So you're given the governing, and the governing has to be filled in. Okay, the governing equation must be filled in. Yes? Here's what I'm going to do. Listen carefully. Example 2 is very similar to example 1. I'm not going to do it right now. Listen. I'm going to go to example 3, but I want you to watch this one over the weekend. Clear? Okay, you're going to probably have to watch one more of these over the weekend also, just so you're aware. We will go over them next week. I'm not going to ignore them. Either next week on Wednesday. I don't think I see you guys. So probably after Thanksgiving. Okay? But keep this in mind that you do need to continue this. So write yourself a note to watch this and take notes. Let's go to example 3, please. A diver leaves a diving platform. Not a diving board, but a diving platform. I differentiate here why. How is a diving board different than a diving platform?
A diving board on the end when you jump off of it.
Yeah, a diving board. Don't you jump on the end and you're like bouncing on the end until you go off the end of the board? What kind of energy do you have when you take this and you're springing up and down? What kind of energy do you have? I'll give you a hint. When you're springing up and down, what kind of energy is that called? You could because your motion is there, but when you're springing up and down,
PES.
PES or PE what? What was the type? What did we call that? What was the word? Yeah, but what was the general word? I said I'm not going to use the word spring. I changed PES to PEE. You remember what E stood for? Elastic. Elastic. A diving board is elastic. What did I define elastic as? Something that returns to its shape, right? Something that's plastic, like a plastic bag, after stretch does not return. A diving board is like a spring. It's like a giant rotational spring. Have you ever pulled on something like a... Oh, what's something that's a good example? That's a good example. There's no good example. Diving board is the best example. I was trying to think of another example where you pull on something and it goes brrrr, and settles back out. Yeah, that's a great one. That's it. And the sound probably helped, right? The sound. So you ever? That's a great example. The door stoppers that come off the wall that are on, they look like conical springs. You know, the spring has like a conical shape to it. It gets narrower. And then the door stopper, if you pull it to the left, it'll go like that. That's what I'm thinking of from a rotational spring. So if we use a diving board, then we can't really ignore the elastic energy in the beginning. I want to get to elastic energy in example 4. So for now, we're not looking at a board, but a platform. Now, the diver leaves the platform with a velocity. With velocity. He's not falling. It's not being dropped from rest. He's not just walking off the platform with no velocity. He's jumping off with a given velocity. So what kind of energy does the diver have in the beginning? If he's jumping off this platform into the water, which is below, what kind of energy does he have in the beginning? Chris? It's definitely got kinetic. There's the velocity at an angle of 23 degrees. He's definitely got kinetic energy to start. And good, Chris. He also has potential. Chris, why does he have potential also?
I just have a question. Wouldn't PES be 0 because the rigidity of the platform is 0?
But I'm talking about PE gravitational, based on the height. You're right, but PES is 0 in this case. Because in this case, K would be infinitely large. K would be infinity. It would take an infinite amount of force to bend it. That's how you think of a rigid platform. Rigidity is K equals infinity, really. Just make a K larger and larger and larger. It's a stronger and stronger platform. So it has potential energy based on its height to start, right? mgy. And it's got kinetic energy based on its velocity to start. Agreed? The question now says, though, if the platform is 8 meters above the water, fine, what is his speed the instant before hitting the water? So the diver dives outward, follow the trajectory, is about to impact the water at this spot, and the question is, what is that value? So what kind of energy does the diver have the instant he hits the water, or the instant before he hits the water? What kind of energy? He's moving still. It's right before he hits the water. Kinetic for sure. Any potential there? Any potential at the end? Yes or no? Both answers are right. Give me a reasoning. Or, I agree, that is correct. If the bottom of the pool is our ground level,
Or if the top of the water is considered ground,
then no. You see what I'm saying? Let's listen to that again. So Isabel said, if the bottom of the pool is considered ground level, when he hits the water, he still has potential energy because he hasn't gotten to the ground. But that makes it more difficult. We have to add in potential energy, right? So if I call the surface of the pool ground level, because where does this problem end? It ends right before the diver hits the surface. So let's call this potential energy equals 0. Make believe that line is flat, please. Make believe it's horizontal. So right before the diver hits the water, he's got no potential energy left. Okay? Does that make sense to do it that way? It just makes life easier. So because he's got kinetic energy at the end, we know that he's got 1/2 mvf squared. So my governing equation, James mentioned a little while ago. What's the governing equation here? What's the governing equation, Sophie? Good. Initial is the beginning. Final is whatever you call the end. Final is whatever you call the end. We care about his velocity upon impact with the water. Let's call that the end. Let's call that the end. How many of you seen This Is the End? Nobody's seen This Is the End? Comedy, James Franco, a couple others? Never mind. 1/2 mvi squared plus mgyi equals 1/2 mvf squared. Why did I jump right into the formulas? Because I know, look, I already listed in the diagram all my stuff. In the beginning, this diver has potential and kinetic. Boom, right here. Potential plus kinetic. At the end, he's only got kinetic. There's no potential needed. So I don't have to write it out every single time. Do you see what I'm saying? Is everybody clear with what I'm saying? Technically speaking, I don't even have to really write this out if I don't want to. If you don't want to. But I would probably do it, at least get some partial credit if you save somewhere along the way. But if you are guaranteed that this is right, go right into that formula and you're good to go. What's in every term? What's in every term? Mass. Why?
Because at every point he has mass.
Yeah, his mass isn't changing. The only formula that doesn't have mass is potential energy elastic, and we'll see how that works. But for now, we can drop off mass. Why am I allowed to do that? Write yourself a note, please, for those that have struggled with algebra a little bit. You can cancel mass because it's in every single term. Term. You can cancel mass because it's in every term. It's like dividing every term by m. If I divide everything by m, the m's all drop off. My goal is once again to find the final velocity of this object. I can multiply by 2. Multiply everything by 2 makes this vi squared. Puts a 2 in front of this. And this makes this vf squared. Again, I'm multiplying the entire equation by 2. Double this, it goes away. Double that, it shows up. Double this, it goes away. And then square root your answer. It gets rid of the square term there. So this is your answer. Take a look. Familiar? You should think so. This is the same answer as the last one, except without this. Look. What happened in the last problem? Wasn't the skater at the top of the ramp released from rest? What would it make VI then? If it's released from rest, what does VI become? So wouldn't this equation just become VF equals root 2GY? And is that what we had, for example, number 1? So this is the same thing. These problems are no different. We've just introduced a little bit of kinetic energy in the beginning, which gives it a little bit of velocity in the beginning, which will change my answer at the end. It'll increase my answer at the end, if anything. Because I'm adding a number to this answer, so my velocity at the end should be more. How many of you ski or snowboard? Let's see your hand. What's that? Ski or snowboard. If you are about to go into a half pipe and you're starting from rest, you'll pick up some speed at the bottom. But what if you were downhill snowboarding or skiing the whole time, and then you enter a terrain park and you already have velocity? Don't you have a lot more energy when you hit that little half pipe or whatever you're going to go into? Because you have initial velocity if you've already been moving. But if you start from rest, you don't have as much energy. That's why that will drop off. Okay, if you drop from rest. James?
Do you put VI on the outside of the back of the square?
Because this is a plus sign. If this was a time sign, if it was VI squared times 2GY, you can move the VI outside as a single VI. Because there's a plus sign, I cannot distribute the square root to each term. It doesn't work that way. Square roots can be distributed to terms, to factors, not terms. Factors, not terms. Okay? Plug in numbers. We'll get a value for V, whatever that turns out to be. I'm not so concerned, honestly, about what that is right now. I'm more concerned about getting to the next one. You got a number? Yeah, I'd appreciate it. Go ahead.
13.2.
Okay? I'm going to take Will's word on that for now. I want to get to number 4, please, though. I would really like to get to number 4. Okay, I want to at least get it set up. You have like a minute or two, not even cheese. Okay, you want to shoot a rubber band across the school junkyard to hit one of your classmates in the back of the head. Okay, you're shooting it from a window that's elevated above the ground 7 meters. Your classmate is 2 meters tall. You know that you can stretch the rubber band a distance of 10 centimeters back. What kind of energy do I get when I stretch a rubber band? Stretch, stretch, stretch is the key word. What kind of potential specifically? Elastic potential. So in the beginning of this problem, I know I've got elastic potential to start. Real quick, I'm shooting from above my classmate, so I've got regular potential energy to start also. I'm launching it. It doesn't give me initial velocity, so there's no kinetic energy to start. I wanted to hit my classmate in the back of the head. Right? I wanted to hit my classmate in the back of the head. So what I can see, it says, what speed will it hit your classmate in the back of the head? So we're trying to figure out the kinetic energy at the end. And if you think about your classmate having a height of 2 meters, we could say there's still potential energy at the end. That's one way of doing it. Okay, if I call the ground level. But if you call your classmate's head ground level, this drops off. Okay, so you really need to do numbers 2 and then finish up 4 and 5. Please, do it this weekend. The homework for 6-3 is due on Monday before you leave for junior retreat. So do it this weekend. Homework is due Monday. Lab is going to be due Wednesday after junior retreat. So if you want to start that over the weekend or after the retreat, that's fine.
How long was the semester?